So welcome to this webinar focusing on the design and modelling of ground source heat pump and VRF systems using DesignBuilder. I'm Dave Cocking, and joining me today to present their project work will be Brendan Hall of CHA Consulting and Mattie DeDoes of Karpinski Engineering. Andy Tyndale will also join us later to help answer your questions. Our primary aim today is to give you a succinct overview of some key considerations when modelling ground source heat pump and VRF systems and how they can be modelled effectively to improve the design process. So although DesignBuilder gives you the ability to undertake all these common forms of building performance modelling and simulation, today we'll be focusing only really on the Energy Plus detailed HVAC tools specific to these systems. Both Brendan and Mattie will be mentioning the importance of considering cost and life cycle costs in their presentations. So I'll point out here that these capabilities and also life cycle analysis are available in DesignBuilder. If you're not yet familiar with DesignBuilder, there are a range of free resources. I just switch to the DesignBuilder website. Here you can see the web page for our new online training content with the various sections. You can access and see all of the available modules using the drop-down boxes there. And a range of free content, including a whole lot of tutorials, a range of past webinars on some really interesting topics, and also a number of case studies. I should point out, for those of you not in the UK, you may want to just filter it to international case studies using this this button here. So all of those resources will show you how DesignBuilder can be used for all of the various analysis types that you see here. We are planning more webinars in the weeks ahead to provide you with new insights into important areas of modelling, including a follow-up to this one by Brendan. And in that, he's going to show you how he used DesignBuilder's optimization tools to optimize a large ground source heat pump system. We're hoping to do that in around 4 weeks' time, so please do keep an eye out for a newsletter related to that. So following this introduction, there'll be two main parts to the webinar. Brendan will cover this ground source heat pump content, and Mattie will cover the VRF systems content. We expect the webinar to last around an hour overall, with ground source and VRF presentations taking around 30 and 20 minutes respectively. And we have allowed time at the end to answer as many of your questions as possible. You can submit questions at any time via the chat box in the control panel, and also by emailing DesignBuilder, Brendan or Mattie afterwards. Their contact details will be on their slides. The webinar is being recorded, so you can review it later if required, and we'll also send you a link to the presentation slides and Mattie's VRF setup guidance. So why a webinar on these topics? Well, it's mostly because we've seen a pretty sharp rise in the popularity and application of these technologies to projects over recent years. Many of the projects need to comply with tightening regional, national energy codes. VRF systems are extremely versatile and they can provide really high seasonal efficiencies over a wide range of climates for a variety of building sizes and types. VRF systems can also significantly reduce installation costs, not least because of the smaller system footprint with the minimized footprint due to pipe duct runs. Supplementing the VRF or heat pump system with a ground heat exchanger helps to further improve the system's operating efficiency and also the system's resilience, especially at more extreme hot and cold temperatures. Energy Plus provides you with the capabilities you need to model these systems with their various performance curves. And accessing that kind of capability is made much faster and easier by DesignBuilder. Within DesignBuilder, you can build an early stage model incorporating a VRF system and still get an appropriate level of accuracy quickly and easily by selecting one of the pre-built templates based on manufacturer's data. The manufacturer's VRF templates in DesignBuilder are primarily provided for fast early stage modeling purposes. But then as your design evolves and manufacturer information for your systems becomes available, you can then either update your early stage system details or you can create a new template using your manufacturer's details. DesignBuilder also provides you with downloadable VRF Curve Generation tools, and you can use those to create your own performance curves for maximum accuracy. You'll hear much more about the systems and their curves from Brendan and Mattie, so I won't say any more on that. Today's webinar is really all about the case studies. So I'm now going to introduce Brendan Hall, and he'll take you through some of the finer points of modeling ground source systems. So if you please bear with me a moment, I'm just going to ask Brendan to present. There we go. Okay, so Brendan is a senior engineer with CHA Consulting in Syracuse, New York. He's a professional engineer with bachelor's and master's degrees in mechanical engineering and has 10 years experience with building energy modeling and geothermal system design. Brendan is also an ASHRAE certified building energy modeling professional and a member of ASHRAE Technical Committee 6.8 on geothermal heat pump and energy recovery applications. So over to you, Brendan.
Thank you, David. Thank you for that intro and for the opportunity to kind of share what our experiences have been with the software. So, like David said, we're going to go through how we've been using the software with designing ground source heat pump systems. So, like David said, I'm a senior engineer with CHA Consulting. We're a full-service engineering, architecture, and construction management firm based out of Albany, New York. We have about 1,300 people in 40 offices, mainly in the Northeast and the Mid-Atlantic, but kind of spread across the country. We serve a diversified market of everything from utility infrastructure to energy to highways to government and institutional buildings and kind of everything in between. Obviously, I work in our manufacturing and energy group, so we focused on building energy efficiency and audits. So, but today, we're focusing on the ground source heat pumps. So as most of you are quite aware, heat pumps are machines used to move heat from a source to a sink. So when we're talking about ground source heat pumps, we're talking about the groundwater, surface water, or some sort of body of water that we're using as our source or sink. In the wintertime, we're using the ground as a heat source, and we're using our conditioned space as the sink. In the summertime, it's the inverse. We're looking Our ground is our heat sink, and our conditioned space is a heat source. And so here's a kind of what the typical deep ground temperatures are in the continental United States. We're located in upstate New York, so ours tend to be in about the low 50s. It tends to be somewhat representative of what your average temperature is year round. So, certainly as we talked about trying to do more all electric buildings, ground source heat pumps are a very attractive option in those areas that have temperature extremes. Especially where we are up where we have very cold winters, and so they can be a better option than even some of the cold climate heat pumps. So when we talk about ground heat exchangers, there are 4 kind of main categories that you'll see. Vertical boreholes are the most common for commercial installations. In more residential installations, you'll see things like horizontal pipe and the horizontal slinkies. If you happen to be near a body of water, then you have a pond available. You can either do that as a slinky or as a plate and frame heat exchanger. But vertical borehole is the most common commercial style, and so that's what we're going to focus on here. The thing that makes designing ground heat exchangers unique is that with most HVAC equipment, really the thing that we care about is peak heating and cooling loads. And that's how we size our equipment. And especially with everything with variable speed drives and variable speed fans, we have a lot of latitude of like how they operate in between those extremes. But with ground heat exchangers, we are very concerned about not only those peak heating and cooling loads, but what the annual heating and cooling loads are. And then when we get into what the actual ground heat exchanger characteristics are, we're talking about, what is the spacing in between your vertical boards? What's the conductivity of the grout that's being used to backfill the boreholes? What's my ground temperature? What are my approach temperatures from my HVAC system? There's a lot of variables that go into it. We're not going to get too into all of the nuances into that because we want to focus mostly on the software. But certainly there are a lot of parameters that you have to take into account. What you're doing though is you're playing with those parameters. There's really kind of 2 basic equations which are shown on the right there that you're solving independently of each other. You're trying to figure out what is the characteristic length of heat exchanger that I need to do my cooling, and then we're repeating that calculation for heating, and then we're looking for what the worst case scenario is between the 2 of those. So that is the basics of what we're doing. Obviously, there's a lot that goes in. You can see how many terms are in those equations. There's a lot that goes into those. One thing we talk about a lot is balanced ground heat exchanger flows. Again, like most system types, we are one of the primary concerns is what is that balance? And when we talk about the loads, we would talk about the loads on the heat exchanger and on the ground itself, because as we show here, I can have identical heating and cooling loads. And if I take average efficiencies for cooling and heating, because my compressor heat is helping me in the heating and it's hurting me in cooling, I have to, for the same cooling load and heating load, I have to reject a lot more heat to the ground. So I need more absorption capability from the ground than I need heat to absorb back from the ground to do the same amount of heating. So what can happen is if you have an imbalanced load or an undersized field, you can heat up that ground as the time goes on. So, the time scale we're talking 10, 20, 30, even more than that years. If that field is undersized, if that load is imbalanced, or if it becomes imbalanced, you will start to see that your temperatures creep up year over year. So like in this example, at year 20, that top line is representing the maximum entering water temperature to my heat pumps. That is now almost 100 degrees. So not only have you lost capacity from your heat exchanger, you lost capacity from your heat pumps. They're now less efficient, and you might even be getting to a point where they're just going to stop working because they will trip on a high condenser water temperature. So the way that we apply this in Energy Plus and DesignBuilder, the the ground heat exchanger, it's a condenser loop component. It goes on the supply side the same way a cooling tower would, with your heat pumps and your kind of building load side being the demand side of the loop. Then we have this, and then we have what this looks like in DesignBuilder with our ground heat exchanger, our supply loop, and then our supply pump, and then our temperature set point. So obviously the backbone is Energy Plus. So in Energy Plus, there's a model that has what's called a G function, which is a mathematical type of mathematical model that is going to determine the thermal response of the ground to a heat pulse. And it looks at it in different time scales because there's a immediate response that we're interested in, like in a kind of daily diurnal cycle, and then we're also interested in a medium term, as like kind of like as a week goes, and we're also concerned about the seasonal, winter time to summertime, that temperature swing as the year goes on, and we switch from cooling to shoulder season to heating and back. So in Energy Plus, it can calculate that G function, but it can do it for a limited amount of configurations. So one of the themes that we're going to keep coming back to is that a lot of different tools do a lot of different things, but they tend to be very good at a limited number of things. So this is where, yes, we can calculate that, but really we want to rely on a more purpose-built, the ground source heat exchanger program to do that. So when we look at building energy model, things that go into it, the envelope, the wall configurations, the window configurations, the system configurations, we're dealing with very complex definitions, and we're doing things on an hour, maybe sub-hourly time step. What we're doing is we're looking at the feedback loops from all these different systems and how they're being controlled. So there's a lot going on in this model. We can also have a very diverse system types and sizing, depending on how our zoning is. But because there were so many points and so much data that we're calculating, we're limited to very short-term simulations, typically a year. When we look at the purpose-built ground heat exchanger design software, the focus is on the ground physics and the heat flows from and away from that ground heat exchanger. So it is looking for hourly or monthly heating loads that you are going to input from a different program. And so it has a very simplified HVAC simulation that will capture some of the changes in performance for part load, but it's a very, very simplified simulation compared to what you're doing in your building energy model. But because we've limited that, we can simulate that much more easily over a long time, like 10, 20, 30, 40 years. So there are a couple common software packages. They're listed at ICSPA, which is the International Ground Source Heat Pump Association. They have a website. They have a listing of the most common software packages and the pricing, and a little more detail of the kind of options that they have. The main ones are Ground Loop Design, GLD. There's GLEPro out of Oklahoma State University, and then there's a web-based one called LoopLink. The two we're going to focus on the first two because those have the functionality to export that ground heat exchanger model into the Energy Plus directly. So one of the things I'm going to kind of keep coming back to is we're going to use this DOE reference medium office building as our kind of test bed to show how this works and show some of the results of what you can do with it. So it's a very typical building, 3 floors, 54,000 square feet, 1/3 glass. It has very simplified zoning. It's got 90.1 2004 constructions. I placed it in the greater New York City area, which is climate zone 4A. When we go to size the ground heat exchanger, we're using our energy modeling program. We want to determine what the loads are in that program, because it's looking for the monthly totals and the monthly peaks for your heating and your cooling loads and how those change over the year. This is the most common method of calculation. However, because we have the data from the model, if we can pull the hourly condenser loop loads, that is a much better way to do it. If we have that, and since we're doing this, in Energy Plus, we have that data available. So the reason for this is, for the same heating and cooling loads, if we go that route and let the ground heat exchanger program simulate the heat pump behavior for different manufacturers, for different models, for different size tonnages. So what it does is it takes that heat pump and it divides your loads out evenly. It assumes that you've just evenly sized them out. They're going to have slightly different part load performance. They're going to have slightly different part load efficiencies or in design efficiencies. So what you're seeing here is there's a lot of variation in the length of the heat exchange of the bore field length that it's saying that it needs to do the exact same loads. Whereas if we take the condenser loads directly from our Energy Plus model, we can, in our Energy Plus model, we have zone heat pumps that are variable sizes. We have a DeDoes unit that is also a heat pump, and that's a much bigger size. And so we can capture that sophistication more directly and have a better answer by directly inputting those and letting it specialize in the ground physics like we want it to, and leaving the HVAC simulation to the program. So you can see where basically all of these other ones now we have excess length that we are that we're forecasting. To give you a mileage marker, every 1,000 feet of that ground heat exchanger is about $15,000. So for example, if you look at that worst case one that's almost 30,000 feet, that's almost 6,000 feet more than what the Energy Plus model is saying. So that's $90,000 right there of ground heat exchanger that you've bought for no reason. And $90,000 in a 54,000 square foot building, it's a little over $1 square foot. That's there's a lot of other things you can do with that to improve the efficiency of your building. The other thing I want to point out, if you are a fan of using the 200 foot per ton rule of thumb, then your sizing would have been there and you'd be undersized. So don't use rule of thumbs, please. This is your public service announcement of do not use rule of thumbs. So as I mentioned, that the two ground source heat programs, once we determine what we want our bore field to look like, we can export that definition into that IDF format that Energy Plus is looking for. The one thing I want to point out with this slide, though, is different programs include more or less parameters. So anything that is not included in there that you want, you have to then go and put that in manually. So GLD, it has 3 or 4 parameters that are not included in the GliPro export. Same thing, the GliPro export has an extra reference ratio that's not included in the GLD. But all the basics are there. There are 2 main parts of what it's exporting. There's the physical definition, which is that top half, and then the G function pairs, which are those numbers are defining what the thermal response of that. And that's really where the value of getting this export is. It would be fairly easy to manually import all the physical definitions, but that mathematical function, you would not be able to do that without like a direct export like that. So what I'm actually going to do is switch over to DesignBuilder real quick to show you how that process works. So we have our system here. So I'm going to go to my condenser loop supply side. So I'm going to add my ground heat exchanger here. go and connect him up. So he's all connected up. So then I will move into this dialog here. This is the default, what comes in when you put the loop in. So there are a lot of great templates that are located here for helping you kind of get started. You're going to want to progress from that into something more specific to your to your installation though. So if I come down here, I go to import. There's a dialog box that has popped up on my other monitor that I will pull up. So I've already exported the definition from a different file. So I'm going to say open. The ground loop heat exchanger data has been loaded. So everything in red is things that have come through. And it's like I mentioned, there's a couple of these parameters that are just not exported by that program. Same thing with this depth of top borehole. So you're just gonna wanna kind of double check that those numbers are appropriate from what is, those numbers will be listed in that program. You just have to kind of go and check them. And so I've checked these previously. And so those are appropriate numbers for what I have. The only other thing I want to point out is when you're doing this grout thermal conductivity and this pipe thermal conductivity, you just have to make sure to check your units. Some programs will do BTU per foot. This one is in BTUs per inch. So it's just obviously, if you're doing everything in metric, you don't have to worry about that. So I'm going to switch back to presentation. So this is there's a PDF that'll come to you guys that'll get sent out that will go over what I just went over. So a couple of the other model inputs to look at is, so there's a design ground heat exchanger flow rate that'll come over from the heat exchanger program. So you're gonna wanna go and at your condenser loop, you wanna set your maximum flow to that. That'll also size that pump if you've auto-sized it for that flow. The other thing is to be aware of what your setup, your pumping scheme is. If you have a primary only loop and just constant volume, and all of your flow is always going through your heat exchanger, you're going to want to delete this bypass that I have pointed out here, because what that bypass is going to do, if you don't do that, is it's going to bypass flow around that heat exchanger to try to control to that control point that exists there. So if your scheme is to always go through the heat exchanger, you want to get rid of that, so you make sure that all the flow always goes through that heat exchanger, and you're capturing that. Because obviously more flow means a higher Reynolds number, which means different heat transfer coefficients, and you want to make sure you're capturing that. So alternately, if you have a primary secondary loop, you want to keep that bypass, because that's going to mimic the behavior of the three-way valve or that you're going to have in there to try to regulate how much flow is going out to that heat exchanger. You can take that one step further. If you have that primary secondary and you want to capture that pumping power, you can also just add the pump into there, so you can capture that a little bit more accurately. So we want to show what the results of this test model were, just so we can show that there is agreement between what Energy Plus is doing and what the ground heat exchanger design program is outputting. So we're going to focus on this scenario here, because one of the questions you could obviously have from looking at this is saying, well, this is saying with all these heat pumps that my heat exchanger should be much larger. Are you sure you're not undersizing it? Which, is a perfectly reasonable question to ask. So I said, let's explore that. So we took the results from that, and using the condenser loop flows, we ran them. We ran that through the ground heat exchanger program, and we ran that through there, and saw that the response from the how the heat's flowing back and forth that matched within within 1%. So we can say with fair good confidence, the ground heat exchanger program for the same loads is saying that our ground heat exchanger size appropriately over that long, 20-year time frame. So we want to take that one step further, because now in more recent versions, Energy Plus can simulate buildings over a longer time frame. So we said, okay, well, let's take that. We're gonna simplify the data we're saving. So instead of an hourly saving of data, we're gonna do it on like a monthly basis, so we can run it out further and not create giant output files. So at year one, the peak of so we're looking at average entering water temperature over a month. So that peaked 0.4 degrees higher than what the ground heat exchanger program was asking. But if you can see, as you go over 20 years, it's tracking that gradual rise in the temperature exactly as the ground heat exchanger program is. So that at year 20, we are still within about a degree, which is pretty good. You can also see that trend that the ground is stabilized. We've kind of created a new normal, so that we're not worried about that long-term heat exchanger form is continuing to run away. Then also, this is an average, so in the data for that max year 20, our max entering water temperature is 85 degrees, which is what our design is. So we're showing that yes, that ground heat exchanger that we said was much smaller than we needed is actually appropriately sized. So I wanted to show kind of how far you can take this. This is a project I did at my previous employer, and they were nice enough to allow me to include this in here. This is also a case study we did for DesignBuilder that's located on the website. This was a 350,000 square foot high school that was 2/3 new construction and about 1/3 renovation. Sustainability is very important to the community, and they, from the word go, they wanted to do geothermal. So that's what we pursued. The building was certified LEED Gold, and the engineering design also was, we got an outstanding achievement award by the American Council of Engineering Companies in Ohio. So we had a hybrid geothermal bore field. We had a 700-ton modular heat recovery chiller that was creating chilled water and hot water for 4-pipe fan coil units, 21 air handling units, and then included in those we had indoor DeDoes units that had enthalpy wheels, and we also had dehumidification heat pipes. So we kind of got to do all of the fun things all in one building. I mentioned we did a hybrid system, so we had 190 boreholes that were 500 feet deep. It was about 18 miles of piping. So the bore field is sized to support all of the heating load of the building, and so that will cover about 60% of the cooling load of the building. So you can see the school under construction on the left here, and then the bore field on the right. While they were in the midst of drilling it, that field would later become a softball field. So what that looks like in DesignBuilder, it was very complex. We had 21 air loops. We had the 5 heat recovery chillers, 6 hydronic loops. We had the ground heat exchanger, fluid coolers for the hybrid. We also had 2 spaces that had displacement ventilation, so it was nice to be able to natively do that in those 2 spaces. And then also we had an natatorium. One thing I wanted to highlight, because it gets used so much with geothermal systems, is simulating modular chillers. So this is actually a trick from back eQuest mailing list days. So this is, Energy Plus doesn't have a heat recovery chiller component in it. So what you have to do is you duplicate each module is a heat pump chiller and a heat pump heater. You can then use the staging for the loops to make sure you don't get odd, unrealistic scenarios for the loading of each of those. Obviously, you can if you have 3 modules in cooling, you can't have also 3 modules in heating. You have to make sure that you're avoiding those scenarios. And then when we were working with one of the manufacturers and generating some custom curves for these, they had also suggested that that curve that is the efficiency as a function of the part load ratio, that is basically constant for units that have scroll compressors, because the way they do the staging is they just stage compressors on and off, and so that they didn't see any change in the efficiency of the unit based on the part load ratio. Now you still see it for changes in condenser water temperature, changes in load temperature, but you can not based on the part load ratio. So as I mentioned, we did a hybrid geothermal system. We ran out of, there wasn't enough open space and not really the budget to do the full geothermal bore field. We reduced the boreholes from about 330 to 190. I think offhand it was saved about $700,000 after you added the cost of the fluid coolers. Replaced the boreholes with supplemental heat rejection in the form of 2 200-ton fluid coolers to help trim the load. And so we ran the model with and without the fluid coolers, and so we calculated that it allowed for about 90% of the energy benefit for about 60% of the cost. They can be a little tricky on the modeling side. The condenser loops don't really get that they are supposed to be helping with heating. It's fine when it's just attached to the ground heat exchanger module, because it gets that it can allow that temperature to float wherever you need it to go. When you need to start putting set points on it, it can be tricky to get those set points to line up right. So there's kind of 2 ways you can do it. You can split the equipment between the ground source heat exchanger and the fluid cores, then use the loop staging on like the chilled water to help make that realistic. Or you can use a water heat exchanger to help with adding that extra heat rejection if the loop starts to get too warm. So what our results looked like, we have the ground heat exchanger temperatures on the top, what our supplemental heat rejection was looking like on the bottom, and then so the fluid coolers were on, or in reality and also in the program, they're on their own loop that was mixing into the main condenser loop. So it was on a secondary loop, so it was allowed to have a temperature that was slightly, the temperature was allowed to float higher on the return side than it would have been otherwise. So that's why you see similar entering temperatures but higher leaving return temperatures. Because the main thing we just want to make sure that we had enough heat rejection. So we were confirming that our ground loop temperatures were not too high, but then also what that balance was overall. And so this is a really useful tool to help us feel a little bit more comfortable with that. So, in summary, we want to make sure that we're using all the tools that we need and we're using them for what they're best at. The energy modeling is such an essential part to doing the commercial ground heat exchangers correctly, and capturing all of the good energy efficiency measures that are being put into these buildings, especially when you talk about energy recovery and things that are driving the loads of the building one way or another. Please don't use rule of thumbs, and that Energy Plus does actually does provide really good accurate ground heat exchanger results, so you can use it with confidence to try to test out different setups and different control schemes, and that you'll get a good set of data set from that. There's a lot more detail on the nuances of how to do good ground source heat pump design. They can be found on in Ashray's bookstore. There's a great book from Steve Kavanaugh and Kevin Rafferty that I have certainly used a lot in my my travels, so I would certainly recommend that.
Okay, thanks for that, Brendan. That was excellent. I get a sense that you've just highlighted some really important design and, more importantly in this context, modeling considerations. And I would imagine that your comments about the eye-watering cost savings from effectively modelling geothermal systems, I would imagine that's raised a fair few ideas in the audience. If anybody watching this intends to use the import capabilities from GLD, GLHE Pro, etc., that Brendan's just discussed, please ensure that you install and use the latest version of DesignBuilder. And the reason I say this is the output format from the other tools can change periodically. And that means the latest version of DesignBuilder is most likely to be able to import the new format. Also related to Brendan's content on the storage and release of heat to the ground, please note that you can run multi-year simulations in DesignBuilder to help capture these effects related to ground heat transfer, and also very thermally heavyweight buildings. Okay, so we'll now switch the focus onto the design and modelling of VRF systems. And these can also be enhanced using a ground loop with heat exchanger. So please just give me a moment to switch presenters over to Mattie. Okay, super. So Mattie has a bachelor's degree in physics and a master's degree in mechanical engineering. And he joined Karpinski Engineering as a building performance and sustainability engineer in January 2018. Mattie's work is mainly focused on energy modelling for LEED and also early design studies of HVAC system alternatives. He's also involved in energy audits of existing buildings and creating building calculation tools to help determine energy savings for individual energy conservation measures. So over to you, Mattie.
Thanks, Dave. So in my portion, I'm going to be talking about kind of how we tie the ground source heat pump capabilities to a VRF, which is a variable refrigerant flow system using DesignBuilder. As Dave mentioned, I work for Karpinski Engineering. We design mechanical, electrical, plumbing, fire protection, and technology systems. Mostly in healthcare, commercial, and education sectors. Our company's based in Cleveland, Ohio, but we have offices around Ohio, one in New York and one in Pennsylvania. My department is the Building Performance and Sustainability team. We do a lot of work assisting our design team in LEED projects and other sustainable design, as well as other energy modeling and calculation, as Dave mentioned. So, how do we get a reasonable model of a VRF system early on in a design project? If a customer wants to know how much is this going to cost me and how much is it going to save me. So I'm going to go through kind of how we can do that using DesignBuilder, how we can show that. So for starters, I'm going to go over the basics of how these VRF systems function from an HVAC design perspective. I'm going to show some of the techniques that Energy Plus uses to model the energy consumption, how to set them up using DesignBuilder, a few important model inputs to note and how they will affect your simulation results. And then at the end, I'll go through a case study where we presented a customer with 4 different HVAC alternatives and showed how much savings could be generated from the VRF system using DesignBuilder. So VRF, as I said, variable refrigerant flow. It functions similar to a heat pump. And this diagram here shows basically a refrigeration circuit between our indoor units and our outdoor units. And the goal of the VRF is to provide sensible cooling and heating to our spaces. Our refrigeration cycle operates such that if a unit needs cooling or if a zone needs cooling, we accept heat from the zone and then we reject it outside. Likewise, if a zone needs heating, we accept heat from outside and reject it indoors. However, where we gain efficiencies in a VRF system is the ability to sort of move heat around our building in the refrigeration cycle without using the compressor to reject all of it outdoors. So at the branch level, we have the capability to accept heat at a zone that needs cooling and then reject that heat to a zone that needs heating. We can also do the same concept at a branch level. So if this branch needs net cooling and this branch needs net heating, we can accept heat and then our refrigerant bypasses the compressor and rejects that heat back into the branch that needs heating, saving compressor energy at the outdoor unit. The diagram I show here is an air-cooled system, but there are two types. There's the air-cooled and the water-cooled. And if I were to diagram a water-cooled system, all it has is an additional loop tied to this outdoor unit. And even though it's still called an outdoor unit, in the water-cooled system, it doesn't have to go outside. But it's basically just our heat pump to move heat from the refrigerant loop to the condenser loop. And this condenser loop can be supplied either by a geothermal system or by a combination boiler and cooling tower. And our supply water temperatures are around 50 to 70 degrees Fahrenheit. So Energy Plus uses a library of curves to show how the performance of these units changes depending on how far we are away from the rated conditions. And if you're familiar with the chiller models, similar to like what Brendan was talking about, it's basically we have our rated cooling capacity and our rated COP, and then these are all just multipliers that say if our temperature is different than our rated conditions, our power is going to be a certain factor times what it would be. And if our part load ratio is different than rated conditions, our power is going to be a certain factor. And this is a runtime factor. So if the compressor has to cycle on and off in one time step, this accounts for that. I only show one curve here. This is the energy input ratio as a function of temperature, which, like I said, provides a multiplicative factor based on the wet bulb temperature of the interior space, as well as the entering condenser temperature. If I slide over to DesignBuilder, you can see that if you go to the VRF outdoor unit, under the cooling and heating tabs, you can see all these curves. So I'll click on that same EIR as a function of temperature. You can see the multiplicative factor is on the y-axis. The x-axis is our interior temperature in Celsius, and the different colored lines represent different condenser temperatures. So as Dave mentioned, DesignBuilder has a library of curves and templates that have been developed based on existing measurements. And these are, even though they're not the exact units you're going to use in your building, they're a great place to start if you don't know what's going in there yet. So I would recommend at least getting familiar with the templates, and I'll go through a little bit how to choose them as you design your building and model it. So in DesignBuilder, I'm going to go through this a little bit quickly in the presentation, but there will be a set of setup instructions provided to everyone that registered. So I encourage you, if you're trying to kind of recreate this process on your own, that you revisit the webinar in tandem with those instructions, and you can go through it at your own pace. So one thing that's a little different with the VRF systems compared to like a standard air system is we sort of have to do a little bit of design of it before we can build the model. And I'll get into what that means in a second. Basically, we need 3 loops. We need our refrigerant loop, our condenser loop, which is the water side, the water cooling, water heating, and then our DeDoes, our dedicated outdoor air. As I said before, the VRFs are only intended to provide sensible heating and cooling, so we also need a way to get outdoor air into the building for ventilation to meet code. I'm not going to go through how to set up the DeDoes in DesignBuilder, but there are resources on their website that will help you do that. So the first thing we're going to do is, after you've got your building drawn and set up, you're going to use the heating and cooling design tools to get a rough estimate for what is the sensible load at each zone. From that, we can basically see how many of those indoor units we need and what size all of those indoor units have to be. By adding up the total heating and total cooling and taking the maximum of all the indoor units on one refrigeration circuit, we can determine we determine the total size of this outdoor unit. And now in order to do that, you got to decide how you're going to divide up these refrigeration circuits between your building. There are a number of ways to do that. Most common are either by occupancy profile. So in this example I'm showing here, we have 4 tenants that occupy 4 separate sections of the building. So they each got their own refrigeration circuit. The other thing is these outdoor units only go up to a certain size. So if you have a very large building, you might just run out of room, like run out of capacity on a circuit. So you need enough. So usually the occupancy profile or the size of the outdoor unit will be your determining factor for how to assign indoor units to an outdoor. So once we have an estimate for the size of all the outdoor units, the next step is to go find a manufacturer. Just go online and look up some people that make these. And for our project, we use Daikin, basically because we want to get some actual data for a unit that exists, not a theoretical concept of a unit. The main data points you need from a data sheet are the capacity and either electric power or COP at rated conditions. Also, for a water-cooled system, we want to know basically the minimum and maximum water flow rates that this unit requires. So going back to DesignBuilder, for each zone group / refrigeration circuit, you're going to put an indoor unit in the zone group and then an outdoor unit outside of the zone group. At the outdoor unit level, you're going to have to select one of these templates. And the choice of template, basically just choose one that most closely matches the size of your units. I think this is 10 tons, and the units I showed you were 12 tons. The curves aren't a whole lot different, and early on in your project, you can see for the water cooled, there's only 5 options. So just get in the ballpark, and that'll give you a good starting point. What we do need to remember to do is for both the capacity and the COP on both our cooling and heating tabs, we want to enter the values we got from the manufacturer's data sheet. Some of the templates will have a different capacity, or some of them might be auto-sized. We want to make sure that the data from the data sheet gets populated into our model for both cooling and heating. Then on the heat recovery tab, be sure to check this box. Some of the templates don't automatically have it checked. And this box enables Energy Plus to factor in performance curves for that recycling of heat around our building, or the moving the heat from zone to zone and bypassing the compressor. Without factoring in these heat recovery curves, our system will operate slightly more like a regular heat pump where it can only be in cooling or only be in heating. And last, on the general tab, we input our maximum water flow rate from the data sheet right here. Moving over to the condenser loop, and I've already got it set up. You can see I basically connect each VRF outdoor unit to a condenser loop that is served by a ground heat exchanger. Now, at this point in our project, if we're early on, you probably don't know the ins and outs of your system, so you're not quite at the stage where you can use some of the techniques that Brendan talked about in his portion of the webinar. So similar to how the templates give us a good starting point for the VRF, we're going to do the same thing for our geothermal system. Basically, you need to choose one of these templates, which is pretty much the same system, just with different numbers of boreholes. So I use a standard estimate at about, for 176 meter borehole, which is about 250 feet, you can reject roughly 1.25 tons out of your loop. That's not a feat, or that's not a number you should go design a system off of, but early on it just gives us a good place to start. So I think this one, using that estimate, was 40 some boreholes, so the next step up was the 60 borehole system, because I wanted to make sure we had enough capacity. The one piece of information you do have to input is this design flow rate, which will go both at our heat exchanger level and, as Brendan mentioned, up at the condenser loop level as well. For the VRF system, this will be the sum of all the maximum flow rates for all the outdoor units. So, regarding a few of the model inputs, at the indoor unit level, you have to select templates there as well. I didn't go into that in the little demonstration. Those templates don't deal with a whole lot of the energy calculations regarding like the power consumption of the compressor, but they do specify or auto size the capacity and airflow. So it is important that you either choose a template that's large enough to serve your largest zone, or use the Energy Plus example template that will auto size that. If you don't, you could model a unit that isn't able to provide enough heating or cooling to your zone and drastically undershoot your energy consumption. The outdoor unit, I mentioned, just pick a template that is near enough to your general size of unit. However, I want to emphasize the importance of specifying the capacities rather than letting them auto size. Basically, if we don't get manufacturer's data and we let that auto size, then all those multiplicative curves that I mentioned earlier, think we are closer to peak conditions than we actually are, because auto sizing will model a unit that's perfectly sized to the peak of our building, but we can't go buy a unit that size because the units only come in certain increments of tons or BTUs or whatever. So I encourage you, if possible, to go find a manufacturer's data sheet and use that data to populate your model. Otherwise, you'll end up modeling a more efficient system than you could possibly install. This little table at the bottom, I just built. It's not by any means a rigorous statistical study, but basically I'm showing that changing the template choice of our outdoor unit yields a smaller coefficient of variation than changing the rated capacity of our outdoor unit when we're looking at annual heating and cooling energies. Now on to the case study. So here we were looking early on in a project at like the pre-design stage at sort of 4 different levels of HVAC systems. We had a constant volume rooftop unit, variable volume rooftop unit, an air-cooled VRF, and a water-cooled VRF tied to a geothermal system. And basically they kind of go from most, or let's see, least cost, least efficient to most cost, most efficient as you go from option 1 to option 4. We then, using DesignBuilder, we're able to get annual energy costs for all these systems, as well as some first costs and maintenance costs, and therefore, over a 30-year analysis length, look at kind of the life cycle cost of these 4 alternatives. Just so happened that due to the size of our building and kind of the placement of it, in this instance, the water-cooled VRF, even though it was more efficient, it wasn't efficient enough to make up for the higher first cost of the geothermal system. We ended up recommending option 3, even though it's not quite as cheap as option 1, because of, you know, better energy performance and also is a little more controllable. We thought it would result in better comfort for the occupants. One note I wanted to touch on in these life cycle cost analysis studies is when we spend a lot of time on the accuracy of our energy model, then all of a sudden the accuracy of our study as a whole is limited by how reliable our cost data is. So I encourage you, if you're doing a study like this, to spend an equal amount of time and effort on getting an accurate cost estimate as you do building an accurate energy model. Just a few places that we used, we referenced the RS Means construction data book that has cost per square foot for a lot of HVAC systems. We worked with our local sales rep, and we also referenced past projects for both price estimates as well as actual costs if they have been installed. So that is all I have. Thank you guys for tuning in. Here's my contact info. Feel free to reach out with any other questions or comments. Thanks, guys.
Okay, great. Thanks, Mattie. I think you brought out some excellent points, and I'm sure they've given everybody food for thought. I personally particularly liked the comparative examples that you provided at the end, and sort of reinforcing the importance of considering life cycle cost as part of your overall design and decision making. So I'm just going to switch presenters now, and okay, so I hope that's given you a good feel for the way ground source and VRF systems can be modelled in DesignBuilder, really to help improve your design and decision making. I'd like to say thank you again to Brendan and Mattie for their excellent presentations, which we really hope that you found interesting and useful.